Hello everyone. Today we're going to deviate a little bit. In the last class we looked at a problem and it wasn't a problem that you'd seen before. Some of you may have noticed that as you were working through the problem. Instead of being a simple mixed integer, it was a location and route problem, something that you haven't done yet. The reason I gave it to you is on your final exam, very likely you will have problems you've never seen before. But you have to take the theory that we've learned and adapt it to the best of your ability. What we're doing is not always necessarily something that you've seen before. Instead, it might be something that is new or something that you're unfamiliar with. For that reason, you do have to be adaptive in terms of applying the theory to the reality when you're solving problems in this class. So what we're doing is we're going to move ahead to transportation problems, and then tomorrow or in the next two sessions, I'll show you examples of A, the homework from last time, and B, a similar example to that. But for now, we're moving ahead to transportations. The one additional reason that we're moving to transportation problems is we do not want a situation where I'm uploading solutions before homework is completed. But I also don't want to upload solutions late by trying to avoid when students can see them. So let's look right now in the first section here. We're going to examine a transportation problem. Now, step one with transportation problems is three characteristics are necessary. And you can see those three characteristics here. Number one, these problems involve transport from a set number of sources to a set number of locations. And the goal is to minimize cost. That is our goal in this situation. We're trying to minimize cost. Number two, each source is able to supply a fixed amount of goods. You do not have unlimited goods. Instead, it's a fixed amount. And number three, each destination has a fixed demand. These three ideas must be present for us to use a standard transportation problem solution. So hopefully we're aware that that is reality and all three must be available. So let's go now into example question one. Let's have a look at example question one. We see that wheat is harvested in the Midwest and stored in grain elevators in three different cities: Kansas City, Omaha, and Des Moines. These grain elevators supply three flour mills that are located in Chicago, St. Louis, and Cincinnati. Grain is shipped to the mills in railroad cars, with each car capable of holding 1 ton of wheat. Each grain elevator is able to supply the following number of tons of grain on a monthly basis. So we see here how much grain is supplied, how much grain is demanded, and the cost of transporting grain from one location to another. Our question is, how many tons of wheat would be shipped from each grain elevator to reach each mill on a monthly basis, while also minimizing the cost of transportation? That's what we're attempting to do here. Now, what we have to do is first visualize the problem. So let's go down, and we see here we're shipping from Des Moines to these three locations, from Omaha to these three locations, from Kansas City to these three locations. That's what we're doing right now. Now the question is, in this situation, how many do we ship from Des Moines to Chicago, Des Moines to Cincy, Des Moines to St. Louis, etc. That's how we're going to formulate our linear programming problem. So going back up here, let's highlight the key points. Wheat is harvested in the Midwest. That's a general area, not important. Stored in grain elevators in 3 different cities, Kansas City, Omaha, and Des Moines. That's our first key piece of information. This is where grain is stored. These grain elevators supply 3 flour mills that are located in Chicago, St. Louis, and Cincinnati. That's our second key piece of information, where the flour mills are. Grain is shipped to the mills in railroad cars, with each car capable of holding 1 ton of wheat. Not important. If each car is identical, nothing important is happening there. Each grain elevator is able to supply the following number of tons of grain on a monthly basis. So this becomes important. This is how much we can supply. Each mill demands the following number of tons. Okay. So looking at our 3 necessary conditions right here. 1, transport from a set number of sources, 3 sources, to a set number of destinations, 3 destinations. Each source is able to supply a fixed amount. This is how much they can supply. Each source is able to supply a fixed demand. This is their demand. And we have a minimum shipping cost. So we have our key cost down here. This is our key information that we've highlighted here. So once we have that information, our first step, as always, is to determine our decision variables. Let's look at our graph. 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 possible routes. That means we have 9 decision variables. We have 9 shipping possibilities. So we're trying to minimize Z, and that's equal to, here for this we have to come up here and we see Kansas City to Chicago is, we'll call it X1A. So let's make this 1. This isn't necessary, but it helps us visualize. 2, 3. I'm just correcting a mistake I made for visual clarity. Okay. Now, we also have A for Chicago, B for St. Louis, and again, we'll make it black for clarity, and C for Cincinnati. So, what we're trying to do is minimize our shipping costs. 1A, 1B, 1C, 2A, 2B, 2C, 3A, 3B, 3C. So minimize, and here we need the numbers, and we have 6x1 plus 6x, instead of 1, we'll call it 1A. And here we have 8x1b plus 10x1c plus 7x1 or x2a plus 11 x2b plus 11x3b plus 4x3a plus 5x3b plus 12x3c. And what we've done is x1a simply represents the name of the shipping route. And we can see that visually above us right now. So let me make all these a little bit smaller so they don't interfere, but the title of the shipping route still stays on our page. That's what we're doing here. Okay, we've successfully compiled our minimization objective function. We're trying to minimize the cost for those 9 shipping routes. But again, and as always, we have constraints. In this situation, we see that we're going to have 6 constraints. That's what we're seeing here. Constraint 1, 2, 3, 4, 5, 6. So our first constraint is the goods shipped from X1. And X1 is Kansas City. So the goods shipped from Kansas City, and that's X1A plus X1B plus X1C. These goods must be equal to 150. And we get this because we know they have 150 available. They cannot possibly make any less than this. They could not ship any less than this. So in the second one, we know X2. So X2 is Omaha. X2A plus X2B plus X2C must be equal to 175. And we see that because we know in Omaha, they only store 175 tons. That's all they can ship. That's all they have available. C3, we see X3A plus X3B plus X3C must be equal to 275 tons. Again, all we're doing is listing the key information that from our third storage site, which is Des Moines, from Des Moines, we can only ship 275. More than that simply does not exist. We're going to do something similar for constraint number 4. We see here for constraint number 4 that Chicago demands 200. So everything shipped to Chicago, which is X1A plus X2A plus X3A must equal 200. That is their demand. Minimize these. Okay, so this is goods required in Chicago. And we can go back and do that the same. Goods can be shipped in Kansas City. Oh, sorry, that was goods can be shipped in Des Moines. Goods can be shipped in Omaha, and goods can be shipped in Des Moines, in St. Louis. So that's what we've shown so far. This is where our demand and supply come into play, because demand and supply controls our decision making. So let's come down here to C5, and we're going to see that X1B plus X2B plus X3B must be equal to 100. And that's goods required in Cincinnati. And again, we minimize just for visual purposes, so it's a little easier to understand. We repeat this one more time with our third destination. So X1C plus X2B plus X3B is equal to 300 tons. And that's goods required. Oh, this was not Cincinnati. This was St. Louis. Okay, and again, goods required in Cincinnati. So here, we've summarized our problem, and we've shown every important aspect of the problem. We know now how we formulated the problem. The only issue at this point is inputting it into the computer. So I'm going to disappear for 1 minute while I upload this information. I'll see you again shortly while we solve this on the computer. Hello everyone, and welcome back. First thing we're going to do today is we're going to solve our problem that we worked out in the previous session using using Microsoft Excel. Now, one of the things that's really important to remember is so far, everything looks very easy using QM. However, one of the limitations of QM is when it comes to data entry. When you have 4 or 5 constraints, QM is very easy. When you have 12 or 15 constraints, QM may be easy. When you have several hundred constraints, QM may not be the best choice. A big key here, and this is very important, is that right now these problems, even if they seem a little difficult for us, don't reflect the difficulty of real problems in a real life situation. Instead, they're kind of beginner problems that allow us to see the possibilities of QM. Allow us to see the possibilities of Excel to solve real world linear programming problems in a classroom setting. But they're not yet real world, because in the real world, there are many, many constraints we have to deal with. So let's start by using this QM using Excel to solve this problem. As always, we'll start by labeling it. This is going to be a little different though. So please, even if you have been following along with Excel regularly, this will be a little different because we're going to look at some things that we haven't really considered. It will be pretty clear now, or will be relatively simple now, but if we were to expand the problem and make it more difficult, bigger, more complex, this approach would be helpful in terms of us solving more complex problems. So we start here, but what we're going to do this time is we're going to go over here and we're going to write mills. If you remember from the problem, we had 3 mills: Chicago, St. Louis, and Cincinnati. Over here, we're going to write in grain elevators. And we've got Kansas City, Omaha, and Des Moines. Now, this is a little different than what we've done so far, but we're going to add a couple more things. We're going to add underneath here demand. And for Chicago, we know the demand is 200. We know for St. Louis the demand is 100. And we know for Cincinnati the demand is 300. That's what we've seen so far. Over here, we've got supply. 150 for Kansas City, 175 for Omaha, 275 for Des Moines. This information was all given to us in the problem. Now, we're going to add 2 more columns that weren't given to us. The first is grain shipped, which is how much was shipped to meet demand. And the next is grain shipped again. How much was shipped to meet demand? How much was received to meet demand? And here we simply add in the very simple equation equals these 3. Right now, we'll make it a little easier. Equals C7 or B5 plus C5 plus D5. And we'll fill down here. What this grain shipped represents is how much was actually shipped. And when we write in our constraints, we'll ensure that this column must meet this column. This cell must equal this cell, and this cell must equal this cell. We do it one more time. So equals this plus this plus this. And we fill right. Now, what we have so far is most of the essential information, but we'll add another one down here. We'll call it cost, because this is, we'll star it first, just for now. We wouldn't normally do this, but I'm indicating with this stars that this represents our objective function. So that is, and this is important, but we won't do it yet because we have one more key piece of information. First, we'll make some of these a little smaller, just so we have plenty of room to work with. We're going to introduce a new Excel function a little bit later, but for now, let's go over here and we're going to write in, and it literally doesn't matter where we do this. We just have to indicate the correct cells later. So here we have we're replicating what we did before. Those are our mills, and here are our grain elevators. And as we know, grain elevators is Kansas City, Omaha, Des Moines. Up here, for our mills, we have Chicago, St. Louis, Cincinnati. Now, all we have to do now is enter our numbers from the previous problem. So we have 6, 8, 10, and we can see that right here, 6, 8, 10. Then down here, we have 7, 11, 11. And again, visible here. And finally, 4, 5, 12. This section here is known as our cost array. How do we figure out what is actually shipped? How do we figure that out? We have to multiply our decision variables, which is what routes we choose. We have to multiply our decision variables by our cost array. So we have to multiply our 3 decision variables, how much will go from each route, by our cost array. So instead of saying equals sum, in this situation, we'll say equals sum product. And in this situation, our sum product is all 9 of these squares. In our situation, B5 to D7. Multiplied by. We do a comma for that. What we're indicating is arrays. I said we had a cost array. That was a decision array. So now we're going to go into array number 2, and I told you already, that is up here. So what we will do is multiply 6 I5 times B5, J5 times C5, K5 times D5. This is solving the problem of entering endless repetitive variables, endless repetitive constraints. When we use cost arrays, and if they are equal, all we have to do is multiply array 1 times array 2, indicated like this, and what the computer will do is it will multiply each of the corresponding cells together, and then it will after it's multiplied them together, it will add all of those products together to give us our minimum cost in this situation. So right now we haven't shipped anything, the number is 0. Hopefully you're following along with that. This will come up again and again in the future. We could have used it previously, but until now it hasn't really been easier. So it's something that we're looking at new, but it is also something that is relevant to what we've been doing. So let's go back, and as always, once all of the relevant information has been entered, once all of the relevant formula have been entered, very simply, we open the solver. Now, as before, when we set our objective, we go to where our objective function is. And that's why I highlighted cost over here. So our objective function is B10. As we remember, with any transportation problem, what we are trying to do is minimize our costs. That's what we know happens again and again. So let's go over here, and we're going to change this to minimization. Now, changing variable cells in this situation, all we're doing is indicating to the computer which 9 cells it should compute. Which 9 cells should it run permutations of? Very simply, we select these 9. Done. B5 to D7. We're going to set it to simplex LP as we always do. And now the last step is adding in our constraints. And how do we do that? We've shown it already. The first one is F5 to F7 must be equal, because we know supply demanded and shipped must be equal, to E5 to E7. So we have 6 constraints. We've entered 3 of them with one very simple step. So we hit add, and now we add our second group of constraints. Cell reference B9 must be equal to a B9, C9, and D9 must be equal to B8, C8, and D8. If they're not equal, everybody does not receive what they want. Everybody does not, maybe potentially all the grain isn't shipped, and ultimately people end up unhappy. What the computer will do in this situation, when we hit solve, what it will do is essentially it will run shipping routes. It will run each route possible to make sure that all the grain is shipped and all the grain is received. It will do that in every way possible. Once it's done it every way possible, it will check all of those solutions and it will choose the one that had the cheapest cost. That is what the computer is doing here. And we've seen that B8 to B9, which is right here, must be equal to the amount demanded. And the amount shipped must be equal to the supply. That's what we've indicated. So we have our objective function. We're trying to minimize costs. We know it's a minimization. We know which cells are being changed, which cells are run permutations of. We also know here what the limitations are. We have to make sure everything is supplied is shipped, and we have to make sure everything shipped is demanded. So we hit solve in this situation. The solver found a solution. All constraints and optimality conditions are satisfied. We hit OK, and we examine our results. This information here is no longer important. What's important is now we can see how much from Kansas City, which had 150, 25 was shipped to Chicago, 125 was shipped to Cincinnati. All grain is shipped. From Omaha, 175 tons are all shipped to Cincinnati. They had 175, all 175 are shipped. In Des Moines, we had 175 in Chicago, 100 to St. Louis, and that's a total of 275, which is what they had, what they shipped. All the grain shipped, all the grain in their possession was shipped. We add them up here, 25, 175, 200 demanded, 200 shipped. 100 demanded, 100 shipped. 300 demanded, 300 shipped. So all of our constraints are satisfied, and we also know we've done it. There are multiple ways to satisfy those constraints. But the key part here, the key aspect of this, is that this was the lowest possible way, lowest possible cost with this cost array to meet that demand. And we did it for $4,525. That is how we solve a transportation problem. What we'll do is I'll very briefly do the same in QM tomorrow before I begin looking at our homework class from last session and then solving another one similar to that. I will tell you now, it is more complicated than we're used to, or it is more complicated than what we've done. And the reason for that is when we do see problems on the exam, I'd like you to be able to adapt what we've studied into what you are expected to produce. So that what you're solving tomorrow is a fixed charge and facility location example. Good luck with that. I do not expect perfection, but I do expect effort. If you are close, no problem. If you are not close, but it looks like you are, again, no, it looks like you've worked at it, no problem. But if you haven't made an effort, if you've done almost nothing, you will have attendance problems. Hopefully everybody's clear on today's lesson. The key point is array 1, array 2, and some product to figure out cost. Anyways, have a wonderful day, everyone, and I'll see all of you in the next session.